Okay. Before we get started, just one quick note. The first day of lecture, I mentioned this class takes 7 hours outside per week outside of lecture and lab. At this point, I think some of you are starting to become believers in that statement. In 7 hours at a minimum, I think some of you are starting to believe that. And we're still getting ramped up a little bit. The homework assignments haven't fully ramped up yet. In lab, we're getting you started on those homeworks and getting going. But this is, of course, a lot of work. I was not just making stuff up on day one. With that said, we have lots of resources to help you out. So just a reminder, office hours, we have them all week. I have mine tomorrow. Come stop by and see me. Piazza, you can ask questions. We have review session going on right now, unfortunately. Yes, I know. Right now until 6, you can stop by after lecture today. We have review session tomorrow, 4 to 6. So check them out. And Friday again after class, 4 to 6. So you can catch that 5 to 6 after class on Friday. This week review session, they're going to go over objects and classes. Definitely good content to reinforce. We only spent one lecture on objects and classes, and unfortunately, there's just a lot of content in this course. We got to move on, but hit up all those resources. Try to get that content. I threw a lot at you on Friday. Try to get caught up, understand all that content. And just a bit of advice, I highly recommend asking questions about the concepts themselves. If you ask a question like, hey, I didn't quite understand how state variables work and how they're updated through methods and things like that, that makes for a much better question on either Piazza, office hours, review session, than the question that we always get hundreds of times per week, which is, I get these error codes, or here's my auto lab output, help, how do I do it? How do I get through this particular question? If you focus on understanding the concepts, understanding those underlying concepts, it's going to serve you much, much better on future assignments. If you're just focused on, I got to get through this lecture question, instead of, I need to understand how this lecture question works, you'll be a lot better off in the long run. If you don't really understand the concepts and you're just getting through the lecture questions, each one's just going to feel exponentially harder until you just get absolutely crushed. Try to understand those concepts. And by the way, myself, the TAs, we love the questions that are more conceptual. How do objects work? What are classes? We love those questions. We'll go to a whiteboard and talk to you for hours about stuff like that. But when it's, how do I do this question? It's not as fun for us, and not as entertaining for you either. And to that end, lecture questions themselves, I mean, I don't even want to do lecture questions. That's a lot of extra work for me, but I kind of have to because I need something to push you all along. If all the questions we get right now are, how do I do this lecture question? If we didn't have those, we'd be getting no questions, and y'all would just get completely run over and crushed by the first homework assignment. But if you fight that trend and focus on the concepts. I don't know. It's advice. A lot of you might ignore it, but it's fine. I just want to make sure that it's out there and that's it. Before we get into new content, anybody have general questions about the course, about anything that's going on? Let's do it. So lectures, got to move on. We always got more content to cover. This course is stuffed if you're not feeling that already. There's a lot going on in this course, a lot of content. So today's lecture question is going to reinforce classes and objects a bit with this pass-by reference that we're starting to talk about. And we're moving on from objects and classes, but whenever I can, I'm going to give something that can reinforce it, that can get the current content and also reinforce something that we've learned. Objects and classes take a while to sink in, and we only have one lecture to introduce it all. So I will try to give more examples whenever I can, but we do have more content to cover. So this one, objects and classes, create a class named team, create a brand new type named team that's going to represent the strength of the offense and defense of a team, and also have a state variable initialized to 0 that's going to store their score. Then we want an object named referee with 2 methods. One that's where the referee is going to officiate a game between 2 teams and determine what their scores are going to be. And this will be a very simple game, very deterministic. Each team's score is going to be their offense subtracted by the other team's defense, with the exception that scores cannot be negative. So if the other team's defense is greater than that team's offense, they get 0 points. They can't get negative points from that. and a declare winner method. So after play game is called and their scores are set, the declare winner is going to read their score variables and determine which one is the winner and return that team as the return value of this method. So in declare winner, you're taking two teams as references. You have two parameters of type team, and you also have a return value of type team. So you're using your new type as both the parameters and the return type. This one has the one condition where if the result of the game is a tie, both teams have the same score, return a brand new team object with offense and defense both equal to 0. So return that team. And one note, I saw this bit on Friday. We had a lot of questions about this on Piazza, so I want to make sure this is cleared up. This is true for all lecture questions, all homework questions, anything, even out there in industry, graduate, and things like that. When you're testing, there's no required testing for this one, if you notice that. But for your testing, which you still definitely do, highly, strongly recommend it, don't test anything that's not explicitly defined in the question. So for example, in this one, if you're creating a new team, you say new team of offense 6 and defense 3, and then your next line is assert that that team's offense is 6 and that team's defense is 3. So if you say like my team dot offense equal 6 in an assert, you're going to run into problems with that because this question, the objective, the problem statement here, does not specify the names of the variables to store the team's offense and defense. So as soon as you do dot offense and accessing that variable, that's going to work fine on your tests because your code has that variable name. But when you submit those tests to AutoLab, you're really rolling the dice on whether or not I named my variables the same exact thing that you named your variables. Now, if the variable name is defined, like score, you can access score and start testing with score. But when it's not defined like offense and defense, how do you know I didn't name those variables team offense and team defense? The only thing that's defined is their types. So you can call a constructor with two values of that type, but you can't access those variables in your testing because you don't know if other developers, in this case my AutoLab, incorrect submissions, you don't know if we have the same variable names. Sometimes you might just get lucky and we happen to choose the same names, but you can't guarantee on that, you can't count on that. So don't access anything that's not clearly defined and explicitly defined in name. You can't access it in your testing. It's true even in industry. If you have another developer on your team, you write tests for them, and you're accessing what you would have named the variables, well, those tests are broken. Those are completely broken tests because they're going to fail even correct code if they just name their variables something different. You don't want tests to fail because of something like that. That's when you're going to get the errors. It won't say test failed on correct and incorrect. That's when you're going to get the errors. Your test had an error on the correct and incorrect solutions. That's the first thing to look at. In office hours, that's the first thing I look at. I see pass your own test, error. I'm going to look at your variable names and make sure you didn't test your variables that you chose the name for. So a bit of a caution on that. Only testing things that are defined in the question. So your tests are being ran on code that you did not write. All right, interpolation versus compilation. So with Scala, there are obviously a lot of differences with this language, but some of the differences are going to be, that you've been feeling so far, are going to be because of this difference, the difference between interpolation and compilation. So let's talk about it for a few slides here. So interpolation, this is when your code is executed one line at a time. Execution starts at the first line of your program. That's executed, the next line is executed, next line is executed, next line is executed. Compilation, by contrast, is where your entire program is translated into another language by a program named a compiler, and then that translated code is interpreted. That is the code that's executed one line at a time. So last semester, Python and JavaScript, those were both interpreted languages. They were interpreted. There's a program running called an interpreter, and the interpreter ran your code one line at a time. In the example I have, these runtime errors were common. If you had errors last semester, there were almost always runtime errors. So in this example on the left, let me point with the mouse. On this example on the left, I just want to point out quickly a little bit of syntax. I'm not holding you accountable for Python class syntax. I want to give an example mostly just to show you, hey, classes exist in Python too. And they're pretty neat. So this is how we define a class in Python. The constructor is not right next to the name like it is in Scala. It's going to be defined by a method very specifically named underscore underscore init underscore underscore. That method is what Python's looking for constructor, and that's going to be what we call to create objects of this type. The first argument to every method, or the first parameter to every method is always self. This is the corollary to this in Scala. It's a reference to the calling object. So self instead of this, but the same idea. And then the parameter list for our constructor. If we want to create state variables, inside the constructor we'll do self dot whatever variable name we want to create. And that's going to create a state variable of that name that we can then access in other methods. We can access that variable because it was created using self.syntax inside the constructor. So we can access that elsewhere. And then when we create objects of this new type that we created, of this class, we do the keyword new, we just call the constructor directly. For Python, they just didn't feel like using the keyword new. I don't know why. I'm sure there's some awesome answer. I don't know why. They don't use new. So for this program, we're going to create a new object of type runtime, for example, with 5 as the initial state. We're going to get that reference to that object, call add to state, print adding to state, add 10 to state, and then print out 15. So this program prints adding to state and then 15 on 2 separate lines. Similar program, with just a slight difference, we're going to do the same thing, create a new object of type runtime error example, except this time when we call add to state, we're going to give it the argument ten as a string. When this method is called, we're going to print adding to state. And when we get to this part, self.state being an int with the value 5, and we're going to add the string ten. These are incompatible types, we can't add them together. So we get an error here, and we get what's called a runtime error. Our program was running. We printed this line adding to state. We actually ran the whole program up to that because we're interpreting this one line at a time. But when we got to this line right here, we got an error. Can't add a string in an int. And then the program crashes at that point. While the program was running, we got an error, and the program crashed. This was common last semester. Your code would run. It's very rare to write a Python or a JavaScript program that doesn't run at all. But once you get to that first error, it's going to crash. By contrast, Scala, Java, C, C++, these are all compiled languages. And in this, we're going to avoid those runtime errors for the most part. You can still get runtime errors in these languages, but we're going to get a lot more compiler errors, which I argue are a lot better. These are a lot better for us. So the compiler is going to look at our code as it's translating into another language. It's going to look at all our code and do a lot of checks for us. It's going to check all of our syntax, make sure everything is using the proper syntax, do have braces where we should have braces, parentheses where we should have parentheses, etc. And it's also going to check all of our types. So here we have a method that takes an int, the same code from the previous slide, just in Scala, not Python. It's going to check our types. This method takes an int. When we call this with the string ten, the compiler is going to say, hey, you said this method takes an int, but you're giving me a string. We can't do that. And what it's going to do, what the compiler is going to do, is give you a compiler error, and it's not even going to run your code at all. We never get to run our code here, because the compiler never finished translating into the other language. So we never even got to the part where we could run. So here we're going to get a compiler error. And the compiler, since it's doing so many checks for us, especially the types, it's going to check all of our strong typing throughout our whole program. It's a lot easier to find errors because the compiler is going to flag you down, and it often tells you the line number and everything. It says, hey, right here you have an error. In our IDs, we'll put a squiggle underneath those errors. We're going to find them a lot easier because that compiler is out there working for us. So it's a lot harder to get those runtime errors. Where runtime errors are very scary because they're hard to find. It's up to us to find them. We don't have the compiler helping us. Sometimes IDEs have nice features that are going to help us find them. But like the error on the previous slide, I don't think most IDEs are going to find that one out. I don't think it's going to catch that one. But the compiler will. So the runtime errors are scary because if you don't spot one of those, or you don't do enough testing and you don't find those errors, it's very easy to put them out to production. Now your users have software that's going to crash on any input that you didn't test that has this error. And that can be very costly, very bad for PR, for your company and things like that. Very bad stuff. The compiler is really there to protect us from that kind of stuff from happening. It's going to flag us down and say, hey, you got mistakes over here. Maybe you should fix those before moving forward. In compilation, this is what's happening when you hit that green go button. You're not just running your code, you're compiling. You hit that button and you get that progress bar on the bottom of IntelliJ. It seems like it takes an eternity for your program to run. That's compilation. That's when the compilation is happening. It's translating your code into another language, and then when it actually runs, it runs like that. I mean, it runs quick. But the compilation is what that progress bar is taking so long to do, is translating this code and doing all these checks for you. In most IDEs, IntelliJ included, it's going to run all kinds of checks. It's going to run that compiler as we're typing to get those errors as they come. Compilers also do a lot of optimization, a lot of kind of fixes for us. So, and this is one of the major advantages of compilation. Besides all the checking that it does for us, it also optimizes. As it's translating into that other language, it can look for ways to optimize our code. So even when we do silly things and waste a lot of memory, and for example, if we have a var and our IDE is like, hey, you declare this as a var, but it never changes. Well, the compiler can make that a value and save us some space if it knows you never actually changed it, but you named it a var. It can do things like that to optimize our code for us. It's really helpful. Makes our programs run a lot faster. But it also can fix some pretty major issues. So this code snippet right here is a recursive function. Again, we'll talk about recursion in more depth later in the semester. But this, we're going to call this recursive function with the value 1, and all this method, I should name it method here, all this method does is call itself with the same input. And it never stops. So what this is doing is constantly creating an infinite number of variables named n with the value 1. And eventually we're going to run out of memory, we're going to fill up our RAM, and the program is going to crash because we don't have any room for any more variables named n. Our program crashes. But with the compiler, with Scala's compiler, it doesn't. Scala looks at this and kind of fixes it and turns this into a sort of a loop. It kind of flattens out the recursion and turns it into a loop, and then executes it like that. So if you run this in Scala, the compiler actually gets rid of this, what we call infinite recursion, and turns it into an infinite loop, which is still bad, but it doesn't crash. It doesn't crash our program. If you're interested in this specific example, it's called tail recursion. It's a nice topic. If you're interested, it's a fun topic to talk about. We'll talk about it regardless when we get to learning objective 3. But if you want to get ahead and check things out, tail recursion is the search phrase. Yes?
What if we added one n plus 1
The compiler would still fix that one. So tail recursion is when the recursive call is the last thing that's computed in the method. So it would compute n plus 1, and then that tail recursive call is still the last call. That recursive call is still the last call, so we'd still tail recursion. It can still flatten that out. But if this was 1 plus recursive function of n, then it can't do that anymore. And then we do get a stack overflow. Yeah, this overflows the stack, which is the namesake of our favorite website. That's when you run out of stack memory, which will make more sense in about 20 minutes, that phrase. Scala compiles, a compiler translates your another language. The language Scala compiles into is Java bytecode. This is the same code code is compiled to, and it runs on what we call the Java virtual machine. If you've ever seen this pop up and said, hey, you need to update your Java, That's your JVM. That's the Java virtual machine saying, hey, I have an update. And if you ever see this pop up, that means you're on a machine that can run Java bytecode, which means it can run your Scala programs. So if you ever see this, you're on a machine on Java, which is billions of devices. Odds are, whatever you're using can run Java. Any laptop, I'd be surprised if there's a laptop out there that doesn't run Java, unless it intentionally just doesn't like Java, I guess. But Java, it's very ubiquitous. Your Scala programs can run pretty much everywhere. Even a lot of embedded devices, for some reason, are running the JVM, running Java. It's very ubiquitous software. Yeah, that billions of devices is not an exaggeration. Java's pretty much everywhere as a JVM. So since Scala and Java compiled to the same language, Java bytecode, then that Java bytecode, by the way, is interpreted by the JVM. So these are kind of hybrid languages. They're compiled, but then they're also interpreted by the JVM, as opposed to some like C or C++. I had a very technical typo on that one slide. C and C++ are compiled directly to machine code, directly to ones and zeros that are interpreted, that are executed by the processor at a much lower level. These languages, they're compiled into Java bytecode, and then the JVM interprets the Java bytecode. So since they both compile to the same language, Scala compiled code and Java compiled code, for all intents and purposes, is the same. It's the same stuff, it's the same language. You can't really distinguish between them from looking at the bytecode. I mean, maybe you could, but the interpreter can't. The JVM doesn't care. So we can mix these languages at will. So we saw this very briefly when I opened up the string class and said, hey, what's the definition of a string class in Scala? And it just said, Scala string equals Java string. And just use the Java string class. So whenever you use a string in a Scala program, you're actually using Java code with that. So you can mix these languages at your leisure, at will. We will actually use some Java libraries, specifically Java FX. It's the reason why we have to have Java 8 installed instead of the latest versions, because they removed Java FX from the JDK. But we will use some Java libraries in this course. We're just going to use the compiled libraries, the Java bytecode, not Java code, Java bytecode, and just use that in our Scala programs as if it were Scala code. It's completely interchangeable at that point. All right, I think that's on that stuff. It's kind of a quick overview on interpretation and compilation. Let's have a chat about memory. This is what we'll talk about for the majority of this week, is this thing right here. So memory, specifically our random access memory on our RAM sticks, is there in our machine. Most people, I would assume, have seen these before. If you ever have your laptop or desktop, you'll see these things. But your RAM is effectively one giant array that can store lots of memory at different addresses, and we have addresses from 0 to the size of our RAM, and we can ask our RAM at any time, give me the value at memory address or memory index, whatever, and it's going to give us the value of that. So it has a random access property, just like arrays. Or arrays, we can say, give me the value at index 5, and it's going to give us that value, and we can jump around the array at our leisure. RAM is the same thing. It's effectively one giant array. Give me the value at this index. It's going to give us that value. Everything in our program is going to be stored in RAM. RAM is much, much faster than our hard drives. Programs will only use the hard drive if they have specific needs, specifically persistence. Last semester we started doing file I/O and databases when we needed our data to live longer than the life of our program. At that point, we would take some of our data, write it to disk, and then our program could end, and we still had that persistence to our data. When with RAM, all the values, everything we declare with val and var and all the data structures, those are all going to be deleted as soon as our program ends. They no longer exist, so if we want our data to persist, we go to the hard drive. RAM is significantly faster than reading from disk. significantly faster. Even if you have an SSD, RAM is way, way faster. And we pay for this RAM. If you want 16 gigs of RAM, you might be spending more for that 16 gigs than a whole terabyte hard drive on disk. We pay for that speed, but worth it. Definitely worth it. Some of you will notice if you make this very particular mistake on the rhyming dictionary. I have a warning about it in the assignment itself. But the rhyming dictionary has, I think, 122,000 words in it. And if you have a loop where for each one of those words, you're reading that entire file again and iterating through reading each line of the file, you're going to timeout and autolab, and your program's going to take forever to run. It's going to take a long time. But doing that similar thing, and that's because you're reading from disk over and over again, reading that file from disk over and over. But if you read that file once and store all that memory, store all that information in RAM and a big data structure, a big map, probably a map of strings to lists of strings. If you're taking that approach, which I recommend, doing the same computation but on that data structure in RAM just goes by like nothing. Like that's quick computations when we're doing that on RAM. But once it's to disk, it's going to be prohibitively slow. So when we start our program, the JVM is going to go to our operating system and say, hey, operating system, I need some of that memory that you control. My operating system is going to control all this, control all our resources. So we're going to request some memory. And the operating system is going to give us some chunk of that RAM stick. We're going to get some small slice of that array. And it's going to say, this is where you can run your program. And right before and after those addresses that we were allocated, there might be other programs using that space. There might not be, but regardless, we're not allowed to access that memory because the OS might allocate that to somebody else, some other program at some other time. So we're only allowed to stay in the bounds of what the operating system told us we're allowed to use. So we get some subspace of this RAM stick, and then some initialization happens. We're going to get some program information to use up some of this space. If you go to the documentation I linked to for this, they talk a little bit about that. It's a bit outside of the scope of 116, so I won't talk about this program data at all. But I am concerned about the rest of this, which is going to comprise our memory stack. And this is where all our variables are going to go in our programs. So the memory stack is a last in, first out data structure. We're going to draw our stacks kind of upside down from what you would think. So a stack is kind of like, if you think of a stack of papers, we can access the top paper of that stack. We can remove from the top. We can add to the top. This memory stack is going to be the same way. We can add new variables to the top of the stack. We can remove new variables from the top of the stack only. But we'll draw the stack upside down. So we'll always start at the top because think of this in memory with memory addresses as an array. The smallest index would be at the top, and then the indices go down as we go, increase as we go down. So the first value would be at the top, and then we're going to add values to the bottom of the stack visually. So it's kind of an upside down stack when we do it visually. A few terminology, we're going to go through an example to drive all this stuff home and make it a bit more sense, but a bit of terminology up front just to let you know what's about to happen here. We have stack frames. Whenever a method is called in our program, we're going to create a stack frame. And this is effectively an isolated environment for our program, for that method call, where it can only access variables within that environment. So inside a stack frame, when we have a method call, we can only access information that's within that stack frame. We can't access the entire program stack. We can only access what's in that stack frame. And our program execution begins with the main method. The main method is called. We get the main method's stack frame, and that's where everything begins, and we'll create more stack frames as we call methods and as we go through the execution of our program. We also have code blocks. Code blocks create different sections of the stack as well, but they're not quite as strict as stack frames. So inside a code block, execution is treated a little bit differently, especially with scoping rules. For variable scope, what variables can be seen by a program at any given time, that's decided by the code blocks and the stack frames. The difference is inside of the block, you can see other variables outside of that block, but not outside of the stack frame. So it's a little bit different between blocks and stack frames. So with that, let's walk through an example. Let's run this code and go step by step and see what's going to happen on this program stack. How are these values stored in memory as we go through this execution? And I'm trying to be pretty language independent. This code happens to actually run as JavaScript code. It's not great JavaScript code because I don't have any const or lets or even vars, but this is valid. All the variables just happen to be global. So it's not necessarily good JavaScript, but it does actually run. To just be completely language independent for this example, just to show the concept of the memory stack. So let's run through this one line at a time and see what happened on this stack. So we get this memory from the operating system, and the first thing that happens when we run our program, our command line arguments are going to be the very first thing that go on the stack. Now again, we won't really use command line arguments in this course, probably not at all, but this is the first thing that goes on the stack is whatever arguments were called when our program was called. So if you call a program from the command line and you give it some extra arguments more than just the program name, those are going to be in those command line arguments, args, that string array in Scala. That's the first thing that goes on the stack. Next thing we do in this program is create a variable named I and assign it the value 5. So that variable is going to go on the next available space on the stack. It's going to go on the top of the stack. So we have a variable named I storing the value 5. We place that on the stack. Next we have our first function call, and we're going to start a new stack frame as soon as we hit that function call. So once we hit this stack frame, those command line arguments and that variable I are no longer visible, they're no longer accessible to us while we're inside this stack frame. When we start a new stack frame, the next thing we're going to do is look at all of our parameters. We're going to create variables for each parameter, create that variable, and assign it the value of each of our arguments. So here, the expression I resolves to 5. 5 is our argument. That gets assigned to this new variable n that we created for that parameter. We create a variable result, give it the value, assign it the value 1, put that on the stack. Again, we're just on the next portion of the stack, but importantly, we're inside this stack frame, this new stack frame for this function call at this point. Then we hit our first code block. We start that code block for the loop. We're going to create the iteration variable I, assign it the value 1 from our initialization, and that is going to go on the stack inside of the loop. So when this ends, when we reach the end and we're destroying this block, that variable I is no longer going to be accessible. After this loop, we can't say print I or anything that we don't have access to I. It won't exist. So we have I inside this loop block. We're going to have a result, a variable named result that we're going to multiply by I. Now the program has to look for a variable named result. Since we're inside a loop block, it's going to start inside this block. And it's going to look on the stack inside this block for a variable named result. And it's not going to find one. So it's going to look outside of this scope. It's going to look at the next layer of scope, and it's going to look through here for a variable named result. And right there, finds a variable named result, value 1, cool. That's the result we're going to use. And then it has to find a variable named I. With I, it does find it inside the loop block. So it's going to use this value for I. That I resolves to 1, result resolves to 1. 1 times 1, yeah, it's still 1. But that's what's set back into result. And notice we do have another I. We have 2 variables named I on the stack. But since this is outside the stack frame, it's not even visible. And plus, we already found a variable named I inside this block. So the search stopped right there. We already found a value for I there. Reach the end of the loop block, increment I. That's the one inside the loop. Check our conditional, still true, we're still running. So we're going to do the same thing again. Multiply result by I is 2 this time. Multiply that, assign it result, and then keep going. Go through this entire loop as we expect. By the end of the loop, result is going to be 120. And I have a little typo here. I should be 6 at this point, so the conditional is true. Or sorry, the conditional is false. So when I is 6, the conditional is false, and we're ready to end this loop. So we reach the end of a code block. When we reach the end of a code block, we're going to destroy everything on the stack that was created after the start of that block. So we're going to go all the way up to the start of the block and destroy everything. That I, it happened to just be I this time, but that variable I, we're going to destroy it because it was defined, it was declared within that code block. Now the next thing we reach is our return statement. When we hit a return statement, that's our cue to destroy this stack frame. So we hit this return result. Result is going to resolve to 120, and we're going to destroy this whole stack frame, that variable n, that variable result. All those are gone. It's going to be replaced with the return value 120. So our whole stack frame just collapses to one single value 120. That's what's returned, and that's what this function call ended up resolving to, because that's what its stack frame returned back to the stack, back to the next level of stack frames, which is the main stack frame here. Create a variable n, assign it that return value, print n to the screen, and that's the end of our program. When we reach the end of this code block, that's the end of our main stack frame, and that's going to wipe out the whole stack. All of that memory is freed up again. We reach the end of our program. The JVM is going to report to the operating system and say, hey, that memory I asked for, thanks a lot. I'm done with it. You can have it back. And all of that, everything for our program is deleted off our RAM stick, and none of it exists anymore. It's all gone. That memory is free to be used by another program. Maybe we're going to run our program again. Maybe we'll run a different program. Whatever. That memory is freed up to be used by somebody else. Question? Does the print statement not use any memory? By the time it returns, it won't have any extra memory on the stack. But internally, it might have some temporary variables it might be using. But by the time it's, for our purposes, after it's printed to the screen, it's going to be freed up. Maybe, so after it's printed to the screen, like the screen itself, is it going to use up memory? Is that the question you're asking? Yeah, sure. Let's go there anyway. Let's go there. So after print is executed, there will have to be something in memory that has that string. Wherever that was printed and displayed, that will have to have memory just to be able to show it to us on the screen. It's not, our screens aren't reading from hard drive every frame. But that will be part of another program. So the print method or function, depending on language, is going to go to the operating system and say, here's some characters, can you put these on standard out, which is an operating system defined stream of characters. It's going to put it on standard out, and then we'll have some other program reading standard out, and it's going to use its RAM to store those values and store its current state of whatever it's printing. So if we're running this in the console, that console program that's running is going to get that standard out stream, and then it's going to use its RAM to display it and store all of the history and everything that's shown as you scroll up in your console, all that stuff. So yeah, it will put something to RAM, but it won't be in our program stack in our program. It'll go through the operating system and go to another program stack, or heap. We haven't talked about heap yet, but it'll go to another program's memory. Any other questions? it depends how you have it all set up. You could have it set up where it's reading the file multiple times, but what you would want to do is read the file once, put it in a map data structure, and then have your other methods read that map directly. As long as you're reading that map, you're not going back to the original file. But that's one of the mistakes that can be made on Rhyming Dictionary, is if your code's set up where it is actually reading the file, creating another brand new map with all the same information, and then accessing that map. It can be sometimes easy to make that mistake. So that time it would be reading the file every time, which is what you want to avoid. Yeah, for Rhyming Dictionary, read that file once, get it in a data structure, and then use the data structure. Data structures are all in RAM, it's all fast. Reading from the files, not so much. All right, so let's look at this example. Maybe run it just to show that it does do what I claim it does. Does print out 120. Now let's play with this example a little bit and see the implications of what we just saw. Why do we care about this as developers? What should we be watching for as we develop? So let's just do a few things. Let's create a variable named result of type int, set it equal to, we'll do 1. This is legal. This is something you can do. With all this stuff I'm about to show in the scoping, one of the easiest ways to get rid of this so you don't have to think about it too much is just don't reuse variable names. But if we did reuse variable names, how is Scala going to handle that? So with this one, we have two variables of named result, but these are two completely different variables because they are declared in different scopes. So this result is declared within this code block. So on the stack, we have the beginning of a code block and then the declaration of a variable named result of type int, assign it the value 1. On the stack, this result is going to be defined in this code block. This result, since it was defined in this code block in a different block, same frame, different block, I can reuse that variable name. Now, when we hit this line result, Scala is going to look inside this code block on the stack and look inside this block for a variable named result. It finds one, it's happy, calls off the search, and never goes out to this result, never finds this result. In fact, my warning here is that this could be veiled because I never changed it, which should be something cluing me into, oh man, something might be here. So this result is never changed because this result is the only one being changed. So I'm just returning 1, destroying this result when the code block ends, destroying result and I. This is the result that remains, so that's the result that's returned. Never changed. Whatever I initialized it to, that is being returned. But this is legal. We can do that. But we can't have two variables with the same name in the same code block. So if I do this in the same block, this is where I get my errors because those two results on the stack look like the same exact variable. They're in the same block with the same name with the same type. How do we distinguish between them? We just can't. Like there's no good way to do that. Similarly, if I name this I, I was panicking there. It's because I changed result to val instead of var. If I name that I, now inside this loop block, we're going to look for a variable I, find it within this scope, within this code block, and never even see this I. The search was called off. We already found a variable named I in this code block, in the for code block. Never find this I. So with this code, even though I have 3 variables named I in this program, just by the scoping rules, the correct value for I, the correct I was being used for each iteration of that loop. So I do get my 120 at this point. However, if I delete this and name this J, for example, this is going to give me an error. Even though I do have a variable named I on the stack, since it's in a different stack frame, I don't have access to it. So this won't, even though there is a variable named I on the stack, it won't find it. This won't compile. I can't run. I don't get past the compilation stage. Compilation completed with an error. I have a compilation error. Fix your error is what the compiler is telling me. Anybody have other questions while I have this code open? Anything else you want to see? All right. So this next example, I'll go over it again slower on Wednesday. I want to at least get through it today. Before that, for a stack, so what's stored on the stack? Doubles, floats, ints, longs, shorts, chars, bytes, and booleans. And that's it. End of list. That's what's stored on the stack. I was careful in my examples to only use these types. And everything else is going to be stored in what we call the heap, using heap memory. Notably missing from this list is string. So even strings are going to be stored on the heap. These types are what we call primitive types. There are primitive types in Java. These are technically objects in Scala, but when the compiler converts this to Java bytecode, it converts it to the Java primitive. So these are going to end up on the stack. Everything else is in the heap. And there's always an exception to every rule. I get sick of saying them in lecture. They're kind of distracting. But yeah, there are lots of differences that can break this rule. But for this class, to understand the idea of a stack and a heap, we're going to ignore special things that compilers do. Different versions of compilers do different things. We can know what's going to be on the heap and stack. For our purposes, these stack absolutely everything else, including every class that you write, objects of those types, heap. I want to remove that example. I want to skip right to this one. I should remove that one from the slides. Not like it. But let's see an example of using heap space. So whenever we use the keyword new and create a new object, we're going to allocate memory on the heap. So what we're doing is saying, hey, that stack memory that we have, it's great and all, but I need to put something somewhere else in memory. I just don't want this value to be on the stack, which is going to be anything other than those types that we listed on that other slide. So when I say new instance of this class, this very simple class here, what I'm going to do, or what the JVM is going to do for me, is talk to the OS and say, give me some more memory. I need this much memory. I have this class, this object that I want to create based on this class. Give me enough space to store this thing. So we get enough space for this instance to store this int. And what new is going to return is not that object that was created. It's going to return a reference to that object, which is going to give us instructions of how to find that memory address of where that object is stored in memory. And this is what we call heap space. Whenever we ask the operating system for more memory after the program starts, after we have our stack, we're going to start asking for more heap space, which is more dynamic. It's dynamically allocated. As the program runs, we're going to ask for heap space as needed. Where we don't have these bounds, these problems of used by another program, heap space, we can just keep asking for more heap space. So now, we create this. New returns the reference. This reference, I just made this up, but I just picked a number. But we're going to get some reference telling us where to find that object, and that's what's stored in our values. That's what's stored in this variable data. We get the reference to that object, not the object itself. Just a roadmap that says, how do I go to RAM and find this object? Now, when we call a method that takes this value, this object as a parameter, we're going to give it that reference. When the method accesses this object, it's going to say variable input, storing this reference. Go follow that reference and find a variable named statevar and add 1 to it. So what I actually did was went to that place in RAM, in memory, in heap space, modified that object, and then when it returns, that whole stack frame is destroyed, but the change is still permanent. The change persists. So now when I say in this different stack frame, even though that whole stack frame is dead, it's destroyed, I still can see that change. Data, go to your memory, go to that reference, go to that spot in memory, access state var, that change is reflected because it was made to the same object in heap space. So this is what